Okay, we are at the last section of chapter 13. Basically, we're going to talk about entropy. So let me dismiss my image and let's get going. Uh, Order tends to disorder. The restatement of the second law of thermodynamics is in natural processes, high quality energy tends to transform into lower quality energy. Order tends to disorder. Processes in nature moving from disorder to order do not occur without external assistance. Um, Energy has to be input into the system in order to bring order into the system. The natural direction is to disorder. Molecules of perfume readily go from the bottle, a more ordered state, to the air, a less ordered state, and not vice versa. You're not going to have the perfume molecules just by chance go back into the bottle. Yeah, I think here's a better example. Let's say we have a box with a little divider. We fill it with red marbles on one side and blue marbles on the other side. We remove the divider. It's in an ordered state. Now we can shake. If we shake this box repeatedly, you're going to get what looks like the bottom. Now we can shake and shake and shake. Let's say we only have 10 marbles in the box, 5 red and 5 blue. Now we can shake it, and there is a chance that we'll get, after shaking it and stopping, we might by chance get 5 red on the left hand side and 5 blue on the right hand side. Uh, you can continue to shake it, and that it might occur again. But the more common would be, let's say, like 3 red and 2 blue, uh, and 3 blue and 2 red on either side. Uh, or I mean, you might have three blue and 3 red on one side, and 2 red and 2 blue. I mean, it's going to be mixed. You increase that to 20 marbles, it becomes more increasingly unlikely. You put 100 marbles in there. Is it statistically possible? Yes. Is it probable? No. The probability is very, very low that with whatever 100 or 1,000 marbles, it's going to separate with all the red marbles on one side and all the blue marbles on the other. Marbles arranged by color depict an ordered low entropy state. But of all possible arrangements of the marbles, the most likely are messy high entropy states, the bottom. That's the bottom photo. Okay, this is a picture of entropy. A house left to itself with weather and wind and stuff is just going to collapse over time. If you're not putting the energy to maintain it, it's going to collapse. Okay, the measure of the amount of entropy, the measure of the amount of disorder in the system is called entropy. If disorder increases, then entropy increases. Entropy can decrease if work is put into the system. Just like I say, maintaining the house, you have to occasionally replace rotten wood on the columns, redo the roof. Left to itself, it's not going to repair itself. As an example of entropy decreasing, living organisms take in food or extract energy from their surroundings and become more organized. Your locker gets messier each week. In this case, the entropy of your locker is increasing, decreasing, or hanging steady or non-existent. Well, the entropy is increasing. If your locker became more organized each week, then entropy would increase. Then entropy would decrease in proportion to the effort expended. You have to put work in to make your locker organized. The net entropy in the universe is continually increasing. It's continually running downhill. We say net because there are some regions in which energy is actually being organized and concentrated. This occurs in living organisms which survive by concentrating and organizing energy from food sources. Energy must be transformed into the living system to support life. When it isn't, the organism soon dies and tends toward disorder. The second law of thermodynamics is a probabilistic statement. A probabilistic statement. Given enough time, even the most improbable states may occur. Given enough time, shaking that box of red and blue marbles, it is probabilistically possible that all red will end up on one side and all blue will end up on the other. For example, the haphazard motions of air molecules could momentarily become harmonious in a corner of the room. That's the same. All the red marbles on one side and all the blue marbles on the other. These situations are possible, but they are not probable. And that's the end of the chapter. There's a few more comments I wanted to take or discuss. Okay, there is a third law of thermodynamics, which states that no system can have its absolute temperature reduced to zero. And then there's also a zeroth law of thermodynamics, which states that two systems, each in thermal equilibrium with a third system, are in equilibrium with each other. So if you have block A, block B, and block C, if A is in thermal equilibrium with B, if they're both at the same temperature, and B is in the same thermal equilibrium with C, then A is in thermal equilibrium with C. Seems like a no-brainer, but that is the zeroth law of thermodynamics. And that's all I want to say about that. And that ends the chapter discussion.